So in today's lecture, we'll see the data center design and interconnection network. Basically, we are going to discuss about how the components of the data centers are arranged and how they are actually managed and how they are actually connected to each other. Like all of us know that data center is nothing but a set of servers. So there are different type of data centers we have, starting from small data center to a very large data center. Each and every data center is having different number of servers. So actually, in this topic, actually, we want to know that if there are different servers available in the data center, how you are going to arrange them in the data center. It is essential to manage the space of the data center. If you arrange the things very nicely, then space requirement is going to be reduced. Also, it is important to arrange them in such a manner that if any fault happen to a particular component, then it should not be cause problem for other components. In that case, also you can see interconnection network is more useful, because if one component is failed, then other components are not reachable at all, or there is no alternate path to reach to a particular component of the data center, then that particular component is of no use. Right? That's why interconnection network is very important to choose a particular network, or you can say topology, to connect these components. So that is the basic purpose of going for this particular topic. So data center is consists of very large number of servers, and again in each and every server, you can create one or more virtual machines. And if you see in the whole, we have if you assign each and every virtual machine to a user, then a number of virtual machines to the user, if you see, it is a very large number, right? So these servers can create VMs, or sometimes servers are also called as the physical machines. So we can create the virtual machines, and sometimes also we need to migrate one virtual machine from one server to another server also. So that's why these servers are connected through huge interconnection network, right? So the connection is such a manner that you can easily move from one component to another component. As we talk about network, also it is depends. It is very important. If the topology or the network is well connected, then transmission of the transmission of, you can say in network terms, we can say packet from one component to another component is becomes easier, right? So in that context, you can see interconnection network plays a very important role. So before arranging these elements, you should know in which network, which network, interconnection network you should use to connect these components, right? But if you see the data centers, so then generally these data centers are placed in a particular location. Like in Indian context, we know we have a data center at Mumbai, and in future we have a data center at Hyderabad, right? Already the setup is done, but it is not enabled in Amazon EC2. So more or less, if you see the Mumbai data center or Hyderabad data center, they are located in a particular location, right? They are not movable from that particular location. Let's say one particular location having some problem, electricity issues, or having water issues, because water is the primary part in the data center, because it is used for cooling purpose, right? So in that context, if you see, the data centers are not movable from one location to another location. Like in for a temporary period of time, if you want to move one data center from one location to another location, data center, one location to another location, it is very difficult. Okay, you have to again set up another data center in another location. but movement from one location to another location is practically not feasible. So as an alternative, what you can do, if we have some movable data center. Movable data center means like you can see our mobile phones, right? Whenever we are at home, our mobile phone is with us. Whenever we are visiting our institute, our mobile phones, we carry our mobile phones. So the location of the mobile phones is changing from one location to another location. So many researchers or many people also thought of this thing that why don't you move the data center from one location to another location? Like if you see in a particular location, many users are interested to get the services, or we have seen that number of user requests generated from that particular location is increasing, then we'll see how to move a data center into that location. If we send, if we transfer a particular data center, or if you locate a particular data center in that location, then definitely the problem is going to be solved, right? Because the latency, the delay is going to be minimized. That's why many people thought of the truck container. All of us seen in national highway, whenever we are traveling in the national highway, we have seen a very large trucks, right? They have a container. Basically, these containers are used to transfer goods and services. Sometimes also we transfer, let's say, vehicles. You can say tractors or cars and other things from one location to another location. So these vehicles actually use as a container. So here they have given an example of a 40 feet truck container, but the size varies with respect to different container. So why they have given this example? If we can set off a data center, let it be a mini data center, not, we cannot say it is a large data center. If we can set a mini data center in this 40 feet truck container, right, then we can easily move from one location to another location. Nowadays also you have seen now people are uh, selling foods in a truck, right, or a container, right? So they can locate today in one location. Tomorrow if there is some issue, they can move from one location to another location. So in the similar fashion, the data center also need to be moved from one location to another location to avoid a specific constraints, like water constraints, or you can say if you go for renewable energy, then it may be related to wind constraints or sunlight constraints, because these are some of the resources where you can generate electricity, right? So we can move from one location to another location without any major issue if it is in the form of a container. And if you see, this is we are talking about a very small data center, right? 40 feet container, it is a very small one, right? But when you see the actual size of the data center, it can be 11 times the size of a football field. All of us seen football field. Imagine if you consider 11 times of that particular field. Imagine that much location. In that location, we can place a single data center. That is a large data center, you can say. But in comparison to that, this 40 feet container is very, very small. Again, there is no typical figure for how many servers are there in each and every data center. But typically, one data center may have 4 lakhs to 1 million number of servers. Okay, that's why how you are going to connect these servers. Which server is going to be neighbor of which other servers, right? That is very much challenging, right? We need to consider that as a interconnection network. The good network interconnection network always gives you a better flexibility. If a particular node is failed, immediately you can migrate to the nearest node, right? Only if there is a connection between these two nodes. So if you consider the small data center, you can consider there are 1000 servers. Okay, that's why the data centers varies with respect to size. One data center is having 1 million of servers, whereas another data center is having simply 1000 of servers, right? So obviously, this component is going to vary with respect to different type of data center. Okay. Now, in order to operate the data center, like we have our laptop, desktop, and mobile devices, right? In order to operate it, we need some cost, right? We need electricity every day. We are charging our laptop and desktop, right? Although we are not measuring the cost of the charging and other things, because we got electric bill for all the electric appliances in a particular month, right? Not with respect to each and every component or usage. But when you talk about data center where you have these many servers, you should know the cost of each and every server, right? If you use a particular server, what is the cost? If a particular server is idle, then what is the cost? That you should determine. So here there is a calculation is given, although this calculation is not only not the standardized one. If you may go to other data center, you may find a different figure. So the approximately monthly cost to operate a 400 server data center. Imagine we talk about this 40 feet container. In this 40 feet container, we have 400 servers. Right? Imagine a very large container. We can keep 400 servers in this 40 feet truck container. Then the network cost you have to pay is $13 per Mbps. This is the cost of all the servers, not a single server. We are not calculating per server. Like Amazon, it is saying 0.0015 USD, okay, per hour. Right. This is for one, you can say virtual machines or a, you can say instance, right? But if I calculate with 400, then you can say multiplied with 400, right? That much will come. So if you want to maintain a data center of 400 servers, the network cost you are getting is $13 per Mbps. Similarly, we have storage cost. The storage cost is $0.4 per gigabyte, right? Apart from this, you have other cost also. Like in order to maintain that, you have some cost. If you go for physical data center, you have in a physical data center we have CCTVs, we have security personals. So they are also taking some amount, right? So all these costs need to be okay. You can say all these costs need to be calculated. Then only you can say per server what is the cost you should charge to your customer, right? Once you give your own assessment, right, how much it is as a data center or as a cloud service provider, if you can estimate what is the cost you are spending towards managing the data center, then only you can charge some cost to the customer, right? And based upon the period of time, the cost is increasing, right? So these costs are also going to be increased based upon the spend we have made on running this particular data center. Yes, these costs are coming under the administration cost. So we should know about all these costs in order to calculate the total cost of the data center, and we can charge some amount to our customer. So this picture shows you a simple data center, which is in fact it is a large data center. So this data center, we can say it is 11 times the size of the football pitch, and this data center it contains 4 lakhs to 1 million number of servers. You can see the size of this data center, and imagine how much power is required to run this data center. Like we usually run our uh, we usually run our machines, right? Like our desktops, or you can say refrigerator, air conditioner. So we consume power, right? Similarly, if you talk about this 4 lakhs to 1 million number of servers, how much electricity is required? That's why if you visit this top500.org website, okay, I told you earlier also, in this website you will find the fastest supercomputer in the world. Okay, the list of fastest supercomputer in the world. So if you visit this website, then you will know each and every supercomputer. Supercomputer is also providing you massive power like data center, right? So you will come to know, right, how much power actually required to run that particular supercomputer. Okay, because that is having a very, you can say, very large number of cores are associated with each and every data center, right? So that is, you can see it around like currently, if you go for the November 2022 list in top 500.org website, then the fastest stop supercomputer in the world is Frontier. Okay, and this belongs to United States. And number of cores in this supercomputer is 87 lakhs 30,112. Number of cores are there. So imagine the number of cores are very huge, right? And if you see the power requirement to run this particular supercomputer is 21,100 kilowatt. This much power is required to run this data center, right? Like we have a supercomputer that is called as Param. It is called as parallel machine. Okay, parallel machine. And the latest version is Param Yuva 2. So if you look into this data center, although it is not having this many cores, because this is the fastest supercomputer, so you can estimate the power of the Param also, right? So 21,100 kilowatt is very high, right? So you have to pay the power cost, like we are paying the electricity cost. You have to also pay the equivalent cost. Let's say per 1 kilowatt, this much you have to pay, and based upon the requirement, you have to again reevaluate it, right? So it is very high. In order to run this data center, this is very high. Again, your resource, if you increase the number of cores, definitely the number of resources, or you can say the number of petaflops, we calculate in teraflops per second or petaflops per second. These are nothing but the units related to the resource. So maximum resource power and the minimum resource power is also going to be increased because increasing the number of cores. But again, at the same time, you have to also look into the power requirements, right? Now, another figure you can see here. Let us consider a data center having only 2,000 number of servers. So you can say it is a medium data center, right? And if you look into the configuration of each and every server is just like a high power machine, right? So each server is having 8 GB of DRAM and 4 1 TB of disk drive. Okay, this is a typical server configurations. Again, each and every server in the data center having a different size. Now, each group, so 2,000 servers, they are actually partitioned into different groups. Groups means you can say clusters, right? So we cannot make them a single cluster. To make a single cluster, if something happened to that, then there is a issue. That's why we have created different groups in the data center, right? So in each and every group, we consider 40 servers. Okay, so you can say around we have 50 groups in the data center, 50 different groups, right? So that you can migrate from one group to another group. One group can be connected to another group, right? We cannot component, you can connect to each and every server. Like if you go for 2,000 servers, and if I ask you, if you go for like a mesh topology, all of you know about mesh topology, right? Like if there are 5 components are there, right? How you are connecting a mesh level? Each and every component need to be connected to other components, right? Like this, right? So how many links are required if there are 5 nodes in the mesh topology? Can anybody tell? How many links are required to connect 5 different nodes in mesh topology? Total, how many nodes are required? How many links are required to connect 5 different nodes? You can count also here. 1, 2, 3, 4, 5, 6, 7, This is 8, 9, and 10. Okay, total is 10. That is nothing but n into n minus 1 by 2. So n is 5 into n minus 1, that is 4 divided by 2. So you will get 10 lines to connect 5 different nodes. So if you go for 2000, 2000 means 2000 into 1999 divided by 2, n into n minus 1 by 2. So if I do it, then it is 1999,000. These many links are required. In fact, you can say 19,99,000 links are required to connect them. So it is not a feasible solution. So, but we can connect if we make different groups. Like here I talked about different groups. In each and every groups we have 40 servers. Then this complexity is going to be definitely this one is going to be reduced, right? So in each and every group we have 40 servers, and they are connected through a 1 Gbps link to a rack level switch. A different type of switches we have. So in order to connect these components, and the link is also varies with respect to uh, two different servers. So here we consider a 1 Gbps link. There is another interconnection the link we are using, that is called as a Mirinet. It is a popular one. You can search about Mirinet. It is also a, popular one, right? So what actually the Mirinet is doing? Mirinet, it is a high-speed local area networking system. Okay, because for a data center, they are connected locally, right? In order to provide the resources, they need to connect globally, but inside they have to connect it very fast. They need low latency and high speed. So Mirinet actually provide you high speed local area networking system. The company who developed Mirinet is called as Miricom, and it is connecting between multiple machines to form computer clusters. And here we are talking about groups. Groups means clusters. So in order to connect them, we can use the Mirinet. Okay. Similarly, you can see we have 1 Gbps ports. Not only that, we need ports. Like in hostel, the internet or local area networks are connected. We multiple nodes are connected through a switch, right? So here we consider a 1 Gbps ports which connect the rack level to the cluster level switch. So we have two level of switch here. One is rack level, just like library, the books are arranged in different rack. These servers are also arranged in rack only, right? There are different way we can arrange these servers. So this rack level switch is going to be connected to the cluster level switch through a 1 Gbps network. Okay, so in order to be faster one, you have to ensure that this speed should be as maximum as possible. In terms of Gbps, if it is having in terms of Mbps, then it is slower one. So gradually we want to increase the speed so that faster we can connect them in a faster way. And we have to also look into different kind of failures. Like we have to see that CPU failure. We have to look into the disk input output failure, network failure. All these failures you have to look into while you are considering the interconnection network. Because through this only you can able to analyze which network policy is better. Like one of the popular measure is called as bisection width. I'll tell you later. This bisection width is going to be analyzed for each and every interconnection network. And by looking into that, you can decide which one is more appropriate one. Which interconnection network is most appropriate one. Like in mesh topology, we have considered one thing is how many lines or links are required to connect the components, right? So here you got the number of lines or components required is like 19,99,000, or here it is 10 in a small example, right? Like that you have to make an assessment and choose an interconnection network for the data center. You have to also look into reliability. Reliability is directly proportional to the number of devices. If you are keeping the more copies, right, the same thing you are keeping in more devices, then definitely reliability is going to be increased. So reliability is always increased by increasing the number of devices, or you can say number of redundant devices. Like earlier we say primary and secondary, right? If primary fails, then secondaries act like a primary. So what we are doing? Secondary is nothing but a redundant device. Instead of primary, whatever primary has, the same thing is there with the secondary. So that whenever there is a failure, secondary will come into the picture, right? So you have to go for redundant hardware. The redundant hardware will help you. Redundant means duplicate. Duplicate hardware will help you to ensure the reliability, right? There is other things also we know that is called as RAID, that is called as redundant array inexpensive disk. All of us know about RAID. In operating system we have studied redundant of array of you can say either independent or you can say inexpensive disk. Okay, what it is doing? This RAID is just like a data storage virtualization technique. Actually, it combines multiple physical disk drive components into one or more logical units. It supports your data redundancy. And different levels of RAID also we have seen, starting from RAID 0 to RAID 6. Okay. RAID 0, if you look into, there is no mirroring in the case of RAID 0. But when you go for RAID 6, higher level, then you can get block level stripping. Okay. So that is more flexible. Right. So if you duplicate this one, then it is going to increase the reliability of the system. Similarly, not only the hardware perspective you have to look into, you have to look into the software perspective also. Because hardware is not only the component that is fed, sometimes software also crashes, right? So we have to keep multiple copies of the data in different locations. Like our email case also, our data is kept in 3 different locations. So if one location is crashed or failed, then we can get the same copy from other locations, so that and overall there is no failure in the system. It is not going to impact the performance of the system. That's why you have to ensure that the same copy of the data is retained in the different locations of the world, right? And if you look into the data center has a raised floor. What do you mean by raised floor? Just like if you see the apartments nowadays, okay? So the ground floor is there for parking, right? And the first floor onwards, the construction is done for construction means I want to say that the different floors or different locations are there. Or different people are staying up to first floor onwards. The construction, main construction, or you can say home construction is done, but ground floor is kept empty. Similarly, in the data center case also, we did follow the same process. The bottom one is kept empty. Why it is kept empty? We can hide the cables, right? Like there is a subject called as computer planning and reliability management, planning and management, computer planning and some management, right? So planning and recovery management or something like that. Okay. So if you see this particular topic here, we focus on how to hide these cables. Like if you see data center, there are so many servers are there. If you show the cables, if you not hide the cables, it looks very complex. It is very difficult to analyze in case of failure. So in that case, you have to hide the cables. Okay, you have to connect them properly, but you have to see also these cables should not be shown to shown out, right? Whenever required, we are going to look into these cables, right? So hiding cables or power lines or cooling supplies, these all are provided from the floor. That's why you need a raised floor. We can hide cable some part you can provide the cooling systems to the data center, and some case the power lines, everything is kept grounded, right? So that is the main purpose why the data center is raised floor. So if you look into this underfloor area, okay, like if you look into floor, we have, let's say, floor slab here, then we'll have floor tiles here. So this is the gap we have for cooling purpose, right? So underfloor area, we will distribute cool area to the server. The server racks are here, right? So we'll provide the cooling to the server area from this particular location, right? And there is a unit in data center that is called as CRAC unit. It is also called as computer room air conditioning. So generally, this CRAC unit is in the either both part of the data center. So what this actually they are doing, they are providing the cool air and removing the hot air from the data center. Like whenever you keep your mobile phone, nowadays also in mobile phone you can see your laptop desktops. After using it for long hour, we see there is a heat in that particular device. Similarly, in the data center case also we have heat, right? So in order to avoid this one, this computer room air conditioning is unit is there. The main objective is to collect the hot air and again put the cool air, or to make the internal temperature cool. So you have to provide cooling to the data center. That's why CRAC unit is there. Yes, you can see hot air produced by the server is back to the CRAC unit. Hot air need to be out, cool air need to be provided to the data center. Like usual temperature of a data of our room temperature, if you talk about it, is 25 degrees Celsius, right? We have a requirement that our computer systems are also run fine if it is used in the room temperature. Okay, but room temperature varies with respect to different location. So in the data center case, you can see incoming coolant is having 12 to 14 degrees Celsius. Okay, in order to make the data center inside the data center cool, so the temperature need to be provided is 12 to 14 degrees Celsius. And this warm coolant in the data center, it is going to return to the chiller, right? So let us see how actually the cooling system works in graphical perspective. Yes, here you can see the cooling system in a raised floor. This is your raised floor, right? So here you can see CRAC unit is there. There is two role of the CRAC unit. One is hot air, another is cold air, right? Hot and cold air circulation happens by the help of this CRAC unit. Okay, so there is two type of arrows we have used here, right? One is for cool air, another is for the hot air. Hot air going to be removed from the data center, cool air is going to be provided from the data center. And these are nothing but different racks, right? Where we can place our data centers, right? So just like library, it looks like a library, right? We have racks of books. So here we have racks of servers to provide services to the customers, right? Okay, so generally these data centers are placed in a location where we have sufficient water. Okay, so like just like we have a river nearby, or we have sea nearby, in that place we can place a data center. Because through air condition you can provide the data center, provide the cooling, but sometimes we go with water cooling. So if you go for water cooling, you have to know that the sufficient water is available in that location. So for which the data center's location, selection of the data center location is also very much important. Right? We have to see the environmental constraints while placing the data center in a particular location. Okay, so now let us see what are the different requirements we have for the data center interconnection network. Okay, like I told you, speed. If I talk about speed, then you will say speed need to be as faster as possible. If I say delay, then you can say delay should be as minimum as possible. Like that, there are different requirements here. So here we consider 5 special requirements for the data center interconnection network. The first one is called as low latency. Low latency means delay should be minimum as possible. That means whenever a customer requests a service to the cloud service provider provide these services with minimum delay or low latency. Okay, it should not be more. Right, that is the first requirement. So you have to connect the components of the data center in such a manner that it will cause low latency. Suppose node 1, okay, wants to communicate with node 50. Okay, connect these nodes, or this the node 1 belongs to one particular group, let's say group X, and node 50 belongs to, let's say, group Y. So what you have to do? So group X and group Y. So you have to connect these nodes or these groups in such a manner that if there is any communication between the nodes or between the groups, then it will cause low latency. The second requirement is obviously high bandwidth. If the bandwidth is increased, then definitely, if the bandwidth is increased, definitely the data communication becomes faster. Then overally, cost matters, right? If you look into the customer perspective, low cost is very low cost attract the customer to use the cloud service provider. So how to get low cost? In order to get low cost, you have to see that with minimum amount, how you can run the data center. Right? If you can run a data center with minimum cost, then only you can provide a low cost to your customer, right? Otherwise, if the charge is very high to run the data center and you are providing low, then that will not provide the gain to the data center, gain to the owner, right? So you have to see that overall cost can be minimized in the if the cost is minimized, then definitely the cost of the service is also going to be minimized. The next requirement is message passing interface communication support. Through MPI, you can connect one component with another components. Sometimes we need 50 different nodes or processors. Sometimes we need 200 number of processors. So you have to see that at a time you can reach to 200 processors. Suppose a big task is coming, you want to divide into small tasks, and each chunk you are going to provide to one server, right? So you have to see that the communication support. If the communication support is good, then only you can divide and can circulate. Otherwise, unnecessary delay will happen, which will not able the providers not able to provide good results or results within a particular time to the customers. Another special requirement is called as the fault tolerance. If any fault occur, it should not impact the overall performance of the system. You do redundancy. You increase the number of components, but ensure that if there is any failure happen to a particular component, it should not be impacting other components, right? Okay, these are some requirements, the 5 requirements we have discussed. There is another factor you have to look into when you go for data center interconnection network, that is called as high bisection bandwidth. That's why earlier I also told you about bisection bandwidth. So each and every parameter either need to be minimized or you need to be maximized, right? So bisection bandwidth, it is high, is essential requirement. That means it should be maximized. So you should know what is bisection bandwidth or why we need high bisection bandwidth. So it says that high bisection bandwidth is the sum of bandwidth of the minimum number of links cut to divide the network into two halves. For example, you are given with a network like this. Okay. Let's say these circles are nothing but the servers, and links are nothing but the links indicate that one server is connected to another server. Now this is a network, right? I'll tell you the minimum number of links you use. For example, you can use any number of links, but you have to find minimum number of links to cut. For example, if I cut this particular link, then this is treated as a different network. This is treated as another different network. I can say this is network 1, this is network 2. So you have to find the bandwidth, sum of the bandwidth it says, of the minimum number of links. Each and every link is having one bandwidth, right? So you have to find minimum number of links you have to cut down to divide this network into 2 halves. Okay. So their bandwidth you need to determine, you have to get this one. Then only you will get the high section bandwidth. Not only this is one of the parameters, there are other parameters are also there that we will see as we proceed to different other components. And that is, we are expecting one-to-many communications. Okay, like a file may be present in one server, but it is accessed by multiple people. Right, like there is a post. You can consider Facebook post, right? In that Facebook post, there is a single post by one person, but many people are able to access that particular post or see that particular post, or they can comment in that particular post. So this is possible by the help of distributed file access mechanism, right? And over a period of time, when the number of customers are increased, over a period of time, when number of nodes are increased or number of requirements are increased, so you need to restructure the network topology. Today, for your organization, maybe the start topology is the best one. All of you know about start topology. But tomorrow, your company needs a restructuring, right? Add some new people, remove some people, then managing becomes different, right? So start topology may not be efficient for you. You can move towards any other topology. For example, I can go for mesh topology, I can go for tree topology, I can go for bus topology and other topology. That's why periodically the network topology also need to be changed. Yes, network topology based upon to expand the data center. Okay, now today your data center is having 2000 servers, but you want to increase it to 5000 servers. So restructuring is required. And load balancing case also it is required. Load balancing says that each and every component should get equal load. No one should be underloaded and no one should be overloaded as well. So in order to balance the load among various customers, you need restructuring. Data movement. Data movement is associated with your low latency and high bandwidth, right? For this also you need the restructuring of the network. The next one you can see here. That is data center owners buy server containers. Today we discussed about the server containers, right? I told you server containers are nothing but just like a 40-foot truck containers, right? So data center owners buy the server containers. In the server container, they have different servers, and based upon the requirement, they can move these containers from one location to another location. Sometimes our requirement is as high as possible, which cannot satisfy by a single container. That means one container having, let's say, 400 servers, but our requirement is 600 servers. What happens? Single container cannot satisfy our requirement. Okay, a single container cannot satisfy our requirement. In that case, what you have to do? Suppose there is a container. Let's say this is a container C1. There is another container, let's say C2. So if the requirement is not satisfied in by C1, then if we have another container C2, then we can connect one container with another container. Okay, so a container is having some kind of switch and cabling, right? Through which one container can be connected to another container. These are external switches or cables. through which you can connect one container to another container. If you consider this container is having, let's say 20 groups, this container is having, let's say, another 20 groups. So total you have 40 groups, right? So not only two containers, you can go for as many as number of containers possible if the resource requirement is very high, right? In that way, you can solve the problem, right? So you can see here that the single container is also not satisfied. That means you are dealing with a very large number of scientific engineering applications. That's why the single container is not satisfied. And fault tolerance says that multiple paths should exist between two servers. If two servers are there, they should be connected through multiple paths. For example, you can see, let's say server 1, server 2, and server 3. So there is a direct path from server 1 to server 2. Okay, server 1 can be directly reached to server 2, or server 1 can reach to server 2 by server 3. So you have to ensure that for each and every server, okay, in order to reach any other server, there should be two or more paths. Because if there is one path is failed, then other path we should follow to connect them, right? So similarly, not only you have to find the path, but also you have to replicate the data. Only path is not sufficient. You have to see that the data also need to be placed in the different location, so that if failure happens in one, then we can continue with others. So replicating data and computing among redundant servers. Not only data, computation also among the redundant servers is also required. Now, you have to also look into, there should not be any single point of failure, which we earlier discussed also in distributed service system, which we call as SPOF. Single point of failure need to be avoided. Okay, single point of failure should not lead to the failure of the entire system. That also you need to look into. And if you come to the switch of switch-centric data center design, so there is two type of switch-centric design. It may be switch-centric or it may be server-centric. So if it is switch-centric, switch are used to connect the servers. So servers are connected to the switch. Like multiple computer systems are connected in a local area network through a switch, or we can say hub, right? So there is a, you can say, one hub may be connected to other hubs, right? And one switch may have multiple ports. Through these ports also you can connect with each other, right? That is called a switch centric. But when you go for server centric, right? So here you have to modify the operating system running on each and every server. Like for each and every server, the operating system may be different. Like we have Linux system, we have Mac system, we have Windows system, right? But when you look into server system where servers are used to connect directly without switch, there you need to modification of the operating system is required. See this example, there your idea will be more clear. So here we consider a interconnection network, you can say, or you can say topology, that is called as a FAT tree. FAT tree. So this is one of the interconnection network. If you have studied parallel distributed computing, you might have known about this FAT tree structure. So here in the FAT tree structure, you can see there is two layers, right? If you look into this topology, you have two layers. So in the bottom layers are called as the hardware layers. All topology bottom layers are the hardware layers. Your hardwares are nothing but your server. Okay. And if you look into upper layer you have edge switch. Okay. Upper layer you are having edge switch. So we can connect the nodes in the bottom layer. Why edge switches are actually used? Edge switches are used to connect different nodes or the servers in the bottom layer, right? So here you can see these are the switches, right? You can see these are the different switches, and these are also switches, right? So, but the name of these switches are different. We call these switches, the bottom layer switches is called as edge switches. Edge means near to the node. Core switches are on top of the edge switches, right? So there is a two-layer structure that I told you here: server, another is edge switches, and a group of aggregation of the switches, edge switches, and their leaf nodes or servers are called as pod. So here we consider how many pods? We consider four different pods. The pod means it should have some switches. Like here we call this is a pod, right? This one is a pod. What it says? We have some switches. Okay. Not only this, there may be some internal switches. Like you can say these are very close to the system, which is used for internal switches. Okay. You can consider three different type of switches. One is core switches, edge switches, and internal switches. So pod contains internal switches as well as edge switches, okay, as well as the servers or nodes. Okay. But while you are doing this particular topology, you also ensure that core switches provide path among different pods. Right? Like if you look into these are the core switches, right? Top one is called as core switches. They are connected to the edge switches, right? And edge switches are connected to your internal switches. Internal switches are connected to your servers. So core switches is providing the path actually among different pods. Like pod 1 want to communicate with pod 2. How it will communicate? For example, this node. How it will communicate? It will communicate with this switch. Again communicate to this switch. Communicate with core switch. Core switch connected to the pod 1. Sorry, pod 0 is this is pod 0. This is server 1 of pod 0. Now it is connected to server, let's say server 5, which is under the pod 1. So it is connected like this, right? Suppose you want to connect with the pod 2, then you can use this link to connect with pod 2. Okay, if you connect like this, then you can go for pod 3, right? So core switches provide path among different pods. You have to ensure that each and every node should connect with other switch. For example, if you look into this particular node, okay, let me represent in different color. Okay, so you can connect like this, you can connect like this, right? Now I can connect with directly to this core switch. Okay, so through this core switch, you can connect to pod 1, you can connect it to pod 2, you can connect it to pod 3. So you have to design the fate tree in such a manner that each and every server should connect to other server which is present in other pod, okay, through these switches. Let it be a switch or it is a core switch. So you have to ensure that multiple paths should be there between any two server. If there is no multiple path, then what happens? If a failure happens, then the entire network is collapsed. Like this dotted one, right? So for example, let's say this one is failed. Okay. So anybody wants to connect to the servers under this particular switch. Still this one is alive. The second one is alive. First one is failed. Second one is alive. Right. So we can connect like this. If this particular, let's say, yes, this node is failed. That's why you connect through this node. Okay. But ensure that, for example, the switch is failed. The switch is failed, then the entire and those nodes are under that particular switch, they are going to be unreachable if your switch is failed. So here I am talking about failure with respect to the nodes. If a node is failed, it should not be impact any particular switch. Okay. So you have to look into if, or you can say this is one is primary, another is secondary. One of them should be connected to the core switch as well as edge switch. So if primary fails, secondary will come into picture. Okay. And with respect to this, you can go for routing table, you can go for different kind of routing algorithms. Okay, whatever you have studied, I think you have studied about DSR routing protocol, AODB routing protocol. Different routing protocols are there to send the packet from one server to another server, right? Yeah, this is the description. Okay, now coming to modular data center in the shipping container. I told you about 40 feet truck container, right? This is just like this one. Okay, you can see this is a truck and we have a container. Okay, so if you have a configuration like this is an example of a movable data center, right? Or we can say modular data center. Okay, so that what happen, any point of time you can move from one location to another location. So this is top towered container in the SGI IC modular data center, and this data center is having 46,080 number of processing cores and 30 PB of storage per container. If this much storage is also not sufficient for serving a set of customers, or you can say individual requirement of the customer, then this ice cube, SGI ice cube, need to be connected with another truck container. That truck container is also not able to provide a sufficient services, okay, fulfill the requirement. Then that container also need to be connected to any other, any you can say any one more container, right? So in this architecture, what happened? One container is connected to another container in order to get the services. So what is the main motivation of modular data center? Power consumption is lower. Power consumption lower means, suppose in a particular location, the cost of the power is also varies with respect to different locations. Like all of you also know that city area there is a different charge, rural area there is a different charge, or you can say village area or any other places there are different charges, right? So the power consumption is reduced if you move from one location to another location. In one location you have observed that the cost is more, but moving from that location to another location which is 10 kilometer away, right, the cost is reduced. Then you have to move to that particular data center. Another is density is very high in the case of this SGI ice cube, right? Because you can see the number of cores are more than 46,000 and storage is 30 PB. So imagine in a single container you have these many cores. Like I told you about supercomputer, it is having 87 lakhs 30,112 number of cores. Okay, if you consider it is 88,000, here it is having 46,000. Okay, this is 86 lakh, right? So, but it is 46,000 cores plus cores. Okay, so if you can estimate that 2 ice cube is equal to 1 lakh, so 2 into 88, 2 into 88, right? How much it will come? It is 176, right? Right or not? Or is it still 160, 69, 176 number of SGI ice cube container is required. So instead of going for a supercomputer having 88 lakhs core, if you want to achieve the same power by considering 46,000 is close to 50,000, you need this many containers, right? So that you can achieve the same power. That's why you imagine that in each and every data center, it is too dense, right? Dense means more components we have to provide the services. Similarly, mobility to relocate the data center. Earlier data center, traditional data centers, they are having no mobility. There is no movement. Moving from one location to another location is not possible. But in this case, moving from one location to another location is very easy, right? Because you have truck containers. Okay, so electricity cost is also reduced. Cooling and water supplies cost is also reduced. For example, if you are getting scarcity of water in one location, you can easily relocate to any other location where water supply is there. Another is cheaper housing for maintenance engineer. Yes, see, the maintenance engineers are also not available in one location. If you are moving to another location, they can also, uh, if you move another location, they can provide the services in that particular location. So if you look into this SGISQ, overall 80%, you can say reduction in the cooling cost. Cooling cost is reduced to 80%. That's why this modular data center is very much popular in comparison to the traditional data center. But there are some issues are also there. Movement is also not only the advantage but also disadvantage also. First disadvantage you can see data integrity. What about integrity of the data? Like the security and privacy policies are with respect to different locations, right? If you move from one location to another location, the security policy is changed, privacy policies is changed. So it questions the primary requirements of the security, like about confidentiality, integrity, non-reputation, and other access control. These things are always a question mark. Then server monitoring is also an important issue related to this modular data center. Security management is also there. And the weather proof, that is important. You have to ensure that it is weather proof, right? There may be a rain also, right? In data center, you can make a permanent setup. If you go for traditional data center, you can make a permanent setup. But as it is a movable data center, making a permanent setup is very difficult. But yes, advantages is it is easy to transport from one location to another location. Now, in this lecture also we'll see that how actually these components are connected to each other. Suppose you are having some data, some number of servers, right? 400 servers or 1000 or 2000 number of servers. How these servers are actually connected. So basically, if you look into this modular data center in the shipping container, okay, so there is a structure we followed there that is called as a BQ. BQ is a high performance server centric network. It is not a switch centric network. Switch centric network, you are connecting switches are used to connect to the servers, but a server centric servers are connected directly to each other. Right? But you need to modify the operating systems on the server. So, for example, if you look into healthcare industry, like this COVID-19 situation, also you can see early days we have very less number of kits available in each and every location to test whether a patient is positive or a patient is negative, right? So, what they are actually doing, like in some location, we are collecting the sample and we send to the district headquarters. Then district headquarters is sending the same thing to the capital hospitals, right? So capital hospitals, the testing kits are there, and they need to process these kits and return the results to the customers or the patients, whether they are positive or negative. So here we are talking about the healthcare industry. Okay, so in order to process these things, you need massive computation power. If you want to keep the records of the customer, you also need some storage. So in fact, if you need computation, storage, network, and other things, it is better to install a data center in that location. Right? If the data center is available in that location, so we can easily do the processing. But we cannot set up a data center based upon the urgent requirement. But if there is a shipping containers are there, we can send some shipping container into that location, okay, so that we can provide massive computation or even the storage to the healthcare industry. Like here, you can see a server-centric B-cube network. Like here you see there are two different type of symbols we have used. One is the rectangle. So these rectangles are nothing but your switch, right? Rectangles are nothing but your, you can consider this as a switch, and circles are nothing but your server. In circle, circle represents your server, or you can say physical machine. Physical machine. Okay. So servers are represented in the form of circle, and switches are represented in the form of uh, rectangle, right? So here we have shown two different layered architecture. Earlier also we have seen, we call that is a pod. I told you pod means it is having switches, also servers. So you can see this is also one type, one pod, pod 0. You can say this is pod 1, this is pod 2, and this is pod 3. We consider there is a identical number of servers in each and every pod. Like pod 0 is having 4 different servers, pod 2 is also having 4, pod 2 is having 4, and pod 3 is also having 4 number of servers. And there is two level of switches. Okay, level 0 switches is close to your server nodes, and it connects to all the server nodes. So you can see these nodes are connected to the servers. Okay, and while you number these pods also, if it is pod 0, then the server number starts with 0. Okay, for example, if I ask you, I have a server with ID 23, then you can say the first ID is 2, indicate that it belongs to pod 2. Suppose I will say 33, and I'll ask you it belongs to which pod, then you can say, see, by looking into the first digit, you can say it belongs to pod 3. So all these, you can say, servers are connected to the level 0 switches. Okay. However, all these are not connected to the same switch in level 1. Okay. So level 1, we are not directly connected. So like here you can see this particular server is connected to the level 1 switch, this level 1 switch. However, the second node, that is second server, is not connected to the same switch. It is connected to another switch. Okay. If you look into the third one, it is connected to another switch. Okay. If you look into fourth one, it is connected to another switch. Okay. So what you can see with respect to different nodes, you can say they are connected to the same switch in level 0, but different switch in the level 1. Their overall objective is to avoid the single point of failure. And also we have to ensure that if a node is failed, it is not going to collapse the switch. Right? You have to see that there is alternative path should be there to reach to that particular switch, or that particular the nodes under that particular switch. So in this way they are connected to each other. In some location also you can see the servers are also connected to each other. Because I told you, if it is a switch centric, then switches are used to connect to the server. But it is not only that. Server centric case, the servers can also connect with each other. Like here you can see 21 is also connected to the 22, 30 is connected to 31. So not only it is switch centric, but also it is a server centric. Okay. So there is no standard rules, but still you have to see that all the nodes, all the server nodes need to be connected to the local level 0 switch, and they need to connect to different level 1 switch in order to provide a better communication between different nodes, right? Finally, nodes will connect to another node. Like sender, we say sender to receiver data transmission, right? Sender is a node, receiver is a node. But in between sender to receiver, you have different switches, right? You have different switches. So you have to see that how faster you can reach from sender to receiver, right? For example, I want to connect to, let's say, this particular switch. What you have to do? You know, 03 is connected to 13. So suppose 0, 0 wants to communicate. 0, 0 can communicate to this switch 0, 0. Switch can communicate to this particular node 0, 3, and 0, 3 can directly reach to 1, 3. But if we maintain a structure with the same switch, like here, all the nodes are connected to the same switch. Again, let's say they are connected to the level 1 switch. Then unnecessarily the latency is going to be increased. That's why they have designed in such a manner that the communication between the nodes is having low latency, and you can achieve low latency by connecting the nodes, one node to another node with minimal effort, right? Now another one you can see level 0 switches are starting with 0, okay, and level 1 switches are starting with 1, followed by their ID. What about their ID? Like here we consider 0, here 1, here 2, here 3. Similarly here 0, here 1, here 2, here 3. Okay, like this way they are connected to each other. Now here you can see the B cube 0 means there are n servers connecting to n port switch. And here there are 4 different servers are connecting to 4 port switch. You can see this switch, it is having 4 ports because there are 4 nodes are connected to each other. If it is a three node, it is not practically possible to connect it to 4 different switch. That's why in order to go for a B cube 0, you have to look into n servers, means 4 servers connecting 4 port switch. Similarly, here we have seen in the top layer we have a B cube 0. This top layer we have B cube 0. Because here also you can see there are 4 different connections. Here also 4 connections. Here 4 connections. Here 4 connections. So in general, what you can say, B cube K, where K is greater than equal to 1, is structured from n B cube of K minus 1. There is 2 important things you can see. N server connecting n port switch. Okay, like suppose I'll tell x of n plus 1, you can do, okay, from, let's say, something related to xn. Once you determine xn, if you want to find xn plus 1, then you have to know the value of xn. Suppose I will say 5xn plus 3. Similarly, if you want to find xn plus 2, it is nothing but 5 into x of n plus 1 plus 3. Plus 3. So, if you want to find one step ahead, you should know the previous step. Similarly, in this case, BQ of K, where K is greater than 1, is structured from BQ K minus 1. In order to know K, you need to know the value of K minus 1. So, if you go for B cube 1, let us go for B cube 1. Here K is equal to 1, right? Is structured from n B cube K minus 1. So, you have to take B cube 0. How many B cube 0? Suppose n is equal to 4. So 4 B cube 0 is required. Like here you can see. I say top layer is B cube 0. How many B cube 0s are there? There are 4 B cube 0s are there. How they will connect each other? They will connect through n to the power k. N is your 4. K is 1. 4 to the power 1. 4 port switch. Right? So there is 4 1 port switch. Okay. 4 to the power 1. 4 port switch, not 1. This is 4 port switch because it is n. 4 port switches are required. You can see there are 4 port switches are required to connect them. Okay. So in order to build BQ1, you have to look into BQ0. In order to go for BQ2, you have to go for BQ1. And in the similar fashion, you have to execute it. Right? Okay. So this is one of the example. But sometimes you can see you need more, because here we consider 4 ports, right? 4 port and 4. That means in total we have 16 ports. Right? If you look into this diagram, we have how many ports? We have 16 ports. Right? 16 ports. But sometimes the requirement is more. So in order to interconnect of modular data center, what we have? We have go for another structure that is called as MDQ. MDQ stands for modularized data center queue. Modularized data center queue. And BQ is used inside a server container, right? But we have also another structure that is called as MDQ. How to build this MDQ? You can connect multiple BQ. It may be BQ1, it may be BQ0, it may be anything. Connect multiple BQ container by using high-speed switches. Like I told you, one container can be connected to another container. Similarly, inside that one queues are there, B queues are there, B queues can be connected to each other. Like here I'll show you a MDQ formation by considering 9 BQ container. We use 9 BQ1 container. Again, BQ1 is generated using BQ0. So 9 BQ container, one container, we consider as a single MDQ. Okay. So let us see how a MDQ looks like. This is an example of a two-dimensional MDQ constructed from 9 BQ containers. Okay. And this containers is just like a matrix. How you represent a matrix? You say first component is 0, 0, second is 0, 1, third is 0, 2, right? Then 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. So each and every one is your BQ. These all are your BQ. So they are BQ1. Okay. How many are there? Total is 9. So you can see total is 9. 9 BQs are there in order to form an MDQ. So let us focus on only one container, right? Once you understand one container, you can understand other container. So as it is BQ1, you need 4 BQ0. BQ1 means you can go for 4 BQ0. Let's say these are the BQs. What you will do? If the container is 0, 0 and 4 nodes are there, then it is 0, 0 for everyone. Their IDs are starting with 0, 0 only. In order to differentiate this one, we have a decimal point, then 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so first 2 digit represents the container name. Next 2 digit represents the server name. Right? So that's why you can see 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1. You choose any random one. Like if you choose this one, container 22. So it is 22.00, 22.01, 22.10, and 22.11. So in this way, they are connected to each other. Okay. So now you have found 4BQ0, right? So they need to actually connect with each other, right? So in order to connect, not only they need to interact with each other, but also they need to connect with the other containers also. Okay, let's say these are nothing but 9 SGI ice cube, right? So they need to interconnect each other, right? Otherwise, how they will process? So for this, we have these interconnections, right? You can see here, these are nothing but the switches. Okay, so these switches are actually connecting. Here you can see it is connected to 0, 0 is connected to 0, 1. Here you can say 0, 0 is connected to 0, 2. Okay, through this one, 0, 0 is connected to which one? 1, 0. Right, and this one you can connect to here. 0, 0 is connected to 2, 0. Okay, so four different switches are directly reachable from the container 00. Four different switches. Again, what you will do once you reach to a particular container, for example, you reach to 01, right? If you reach to 01, so from 01, what you can do? You can reach to 02, you can reach to 012, you can reach to 11, 012, you can reach to 21, right or not? And 01 is connected to 00, right? So like that, if you see through some intermediate container, you can reach from one container to another container, right? So if you see this structure, like here you can see, if you look into this particular row, you have two nodes, one is 0000, 0010. So what you can say, overall representation, you can say 00 point, this is star 0. Star may be any value. If you want to combinedly write this one, 00 is common for both. However, here the digit is changing either 0 or 1. So we write star 0. Similarly, in the second row, we have 0001, 0011. So first two is as it is and last digit is as it is, but this digit is changing. So we are writing star 1. But if you go for a column wise if you go for, then it is, if you go for this particular column. Okay. So 00000001. So this is changing. So you can write 00.0 star. Second column wise 00100011. So you can write 001 star. Okay, that represents the second column. Like that you can connect. And there is a small mistake in this representation. Here, the nodes are represented in the form of 00. It should be not like this. There is wrong representation. You can write 11.00, 11.01, 11.10, 11.1. In this way, you can represent 9 different BQs using a two-dimensional MDQ. Okay. Now, let us see some of the management issues related to the data center. Okay. The first issues is related to making common users happy. Right. You have to see that how to increase the number of customers they are requesting to your data center. Right. If number of requests are not increasing, that means users are not happy. You have to give offers like Amazon case. You know that it is free for first 1 year. Sometimes some fees also waived by Amazon. So our overall objective is to make the common users happy. Similarly, control information flow. So information flow, if it is happen between these nodes as early as possible, that indicates that they are highly available. Right? If the nodes are highly available and the communication speed is very high, okay, bandwidth is very high, and definitely you can say the data can be reached from one node to another node without any interruption. Then multi-user manageability. One PM consists of multiple PMs, right? So managing multiple user is also really challenging because you have to maintain the traffic flow. You have to also look into the database updation and server maintenance of each and every user. So managing different user into a single platform is really challenging. It is also one of the issues. Scalability to prepare for database growth. So scalability is not required in terms of computation and storage. It is also required with respect to the database. If the number of customers are increased, if you are increasing the infrastructure, then also you have to see how to increase the power and cooling also. Right? Like in a particular, you can say room, you have 5 servers. Suppose you increase 5 servers to the 15 servers. So now the cooling also need to be increased. Otherwise, it's prone to failure. Similarly, reliability in virtualized infrastructure. So we have failover techniques. Like if one is failed, then another is going to take the role and till that particular system is going to be active, okay, or recover from the failure. We have fault tolerance mechanism. We have VM live migration. Live migration without any interruption, you can move from one cloud to another cloud or one physical machine to another physical machine. So overall, you have to look into a solution where customer will not feel that the service is high costly, right? If the service is having high cost, customer will continue with the traditional infrastructure. Customer will not move to the cloud. So you have to find a reasonable solution. So in order to make both user and provider happy. Okay. Similarly, we have security enforcement and data protections. You have to protect the data that is available in the data center. It should not be available to any unauthorized user or any third party, that you have to ensure. And finally, you have to look into green IT. Green IT says that most of the data center actually runs with the non-renewable energy. The non-renewable energy is called as a fossil fuel. Okay. So fossil fuels includes our oil, petrol, diesel, you can say. It related to gas, it related to uh, you can say other things which is harmful, and which is harmful to not only the environment, but it is also harmful to human body also. Okay, or it is generating some kind of gases that is also leads to some kind of issues related to human being. So in order to avoid that, most of the data centers are run by this fossil fuel. Okay, they generate electricity using fossil fuel. Like we have generators, right? Generator, we use kerosene or petrol and diesel to run the generator, and through which the electricity is generated. So, but it is again generating carbon dioxide, you can say carbon monoxide and other things, other harmful gases, which is harmful to environment as well as to human being, right? So, in order to avoid that, people have come up with renewable energy solutions. In renewable energy solution, what they will do? They will focus on the solar energy. Like most of the street lights are nowadays powered with the solar energy. So daytime it is charging, night time it is using the battery. Using the battery, it is showing the light, right? So that is also one of the movement related to the green information technology. Now, irrespective of that, when you are dealing with multiple cloud or managing the resources, you may face this kind of problem. So this is related to inter-cloud resource management. So you can see, I am showing you here, there are three different cases for cloud resource provisioning without elasticity. Suppose scalability is not there, elasticity is not there, right? So you cannot scale it to 10 different server or 20 different server or 5 different server over a period of time. So you may face a different kind of problem. One of the problem is called as over provisioning, another problem is called as under provisioning. So with these three figures, you can get the idea of the over provisioning and under provisioning concept. See here, the x-axis represent the time in any time unit. Here they have considered the time unit is days, and y-axis represent the resources. Right? Suppose you want to run a particular organization, so you need some resources. So you have some demand to the particular cloud service provider. Suppose you requested, your demand is going to vary, right? Demand is not constant. Any case, like if you go for a website, Flipkart, Amazon, you go for e-commerce website or go for social networking website like Facebook and Twitter and others. So the demand is not going to be same over a period of time. Demand will always fluctuate. But capacity you can decide. For example, here you can see, suppose capacity I have taken, let's say 10 different servers. I consider 10 different servers. So I have requested Amazon to provide 10 different servers over a period of time. Okay, or let's say for 30 days, 1 month period. And I have observed that my demand goes like this, right? Sinusoidal wave, right? So what I observed here, somewhere I am the capacity is equal to demand, right? First case, some case the capacity is equal to demand, and some case capacity is higher than the capacity is greater than the demand. For example, if you look into this particular point, so capacity is higher than the demand. Third case, is capacity is less than the demand? In the first case, answer is no. Demand never exceed the capacity. Okay, demand never exceed the capacity. You can say there is a wastage of resource at this point, there is a wastage of resource in this point, right? That is true. But in none of the cases, the third condition occur in this case. But yes, sometimes we reach capacity is equal to demand, right? So provisioning of the peak load, we consider the peak load in some kind, but the peak load will not sustain for a longer period of time, right? Suppose in a social networking website, you can say 200 customer visited now, and gradually it is decreasing, and let's say after 1 hour again it is increasing to 200, and we have taken, we have estimated that capacity is 200, right? Now if you go for under provisioning, in the second situation, here if you look into this case, capacity is equal to demand, right? And this particular case where capacity is greater than demand, but if you look into this particular point where demand is more than the capacity or capacity is less than the demand, okay, capacity is less than the demand, right? Capacity is less than the demand, right? Your requirement sometimes it is high and sometimes it is low also, so we can say that is called as under provisioning. Similarly, in this third case also you can see some case it is exceeding, the demand is exceeding, some case your demand is equal to the peak demand, okay. So you can see these slots your capacity is not properly used, sometimes it is over provisioning, these times sometimes your capacity need to be high in order to supply the demand, right? But as it is not available, you are not able to provide it. Similarly, in the third case, here the demand is very high. We need to increase the capacity. Here also you need to improve the capacity. Last case, it is meeting the peak demand. So there are different types of situation may happen when you go for the resource management. So by looking into this thing, you can see there are three resource provisioning methods. First method is called as demand-driven method. Okay, so it provides static resources and used in the grid computing. Suppose you will say my demand is 10 servers over a period of time. So you have taken a static resources of 10 server and used for that particular period. So generally this type of resources are used in the field of grid computing. But there is an event-driven method. So in the event-driven method, what we are doing, we are predicting the workload by time. Just like you can say peak hour and off-peak hour. We observe that a peak hour case, the demand is more, off-peak hour, the demand is less. So we predicted the workload and based upon that, we have set the capacity. Third one is called as popularity-driven method. Popularity-driven method uses the internet traffic. It looks into internet traffic, looks the load. Based upon that, it is selecting the capacity. For example, if you see this particular picture, it is becomes more clear. The first one focus on the demand driven, second one is event driven, third one is popularity driven. Again, here there are three axes. Okay, x-axis represents the time. Okay, time means you can say number of days, number of minutes, something like that. Y-axis represent the CPU utilization. And there is a z-axis also. There is a third axis that represents the number of nodes. right? And here you can see there are two color. The graph represents two color. One color represents the CPU load, another represents the number of nodes, right? So if you go for this is a experiment done in Amazon EC2. Okay. So in EC2 performance is analyzed by considering all the three methods: demand driven, event driven, and popularity driven method. Okay, at the University of Southern California using these resource provisioning methods. So if you go for demand driven method, here you can add and remove the computing instances based upon the current utilization level of allocated resources. For example, utilization reached to 90%. For example, okay, then you can add the resources. If utilization is below 30%, then you can remove the resources. Okay. And when a resource has surpassed a threshold, so this is the threshold we fixed here, right? Let's say this is tau 1, this is tau 2. So whenever a resource has surpassed a threshold for a certain amount of time, this can increase or decrease a particular resources. If it is exceeding threshold, let us take a common threshold. Let's say I'm saying 50%. If it is above 50%, add the resources. Below 50%, remove the resources. Either use two threshold by saying greater than 90%, add it. Less than 30%, remove it. Or choose 50%. Greater than 50%, add it. Less than 50%, either remove it. So this scheme will not work if the workload changes abruptly. For example, today now it is 50, then 51, then 52, then 49, then 50, 51, like this. There is an issue. That's why they have considered 20 virtual machines to observe the performance of the demand driven. So they observed that in the beginning phases there is a heavy fluctuation, but after that it is stabilized. Okay, you can see it is stabilized over a period of time. But if you go for event driven method, okay, here also we add and remove machine instances, but not based on the threshold, based on specific time of the event. Some of the events you can say event means some popular days, like you can say vacations, or you can say a specific puja, right? Or specific festival, or you can say Christmas, you can say Lunar New Year in the East, West side it is Christmas. Okay, there you can add and remove resources based upon the event. Like Big Billion Day, the Great Indian Sale, in that case, we can increase, decrease based upon the time. Okay. So our objective in the event driven is you have to achieve quality of service with minimum loss. But again, there is a wasted of resources because in the events that do not fix a particular pattern. In one event, you can see there is a sudden peak. Another case, that peak is not achieved. That can also happen in the event driven method. But if you go for the next method, that is called as popularity driven provisioning method. So here, this scheme anticipates the increased traffic with popularity. Like you have seen nowadays, people are talking about ChatGPT, right? ChatGPT case, the popularity is increased. Okay, this period that you can see many people are interested to know about ChatGPT. So here our objective is to minimize the loss of the quality of service. But again, if the traffic is not following, like previous case, as I said, if there is no fixed pattern in each and every festival, then also it is issue. In this case, also in popularity driven, you can say if the traffic is does not occur as expected, then you can consider the resource may be wasted. Okay, then you can think about the dynamic resource deployment, right? Instead of using this resource provisioning technique, that is demand driven, event driven, and popularity driven, why not go for the dynamic resource requirements, right? So Professor Buya and his team in Melbourne University, they consider a infrastructure that is called as intergrid gateway. Okay, they developed this infrastructure using Java framework. So this IGG actually allocates resources from a local cluster to deploy application in 3 different steps. First one, the customer has to request the virtual machines. Second is it has to examine the virtual machine and check whether we can approve the leases or not. If the resource is available, then only you can approve the resources. If resource is not available, then you cannot approve it. Third is if the resource is approved, then we have to deploy the virtual machine in a particular physical machines, right? So if there is a peak demand will be there in demand driven, event driven, and popularity driven also. Here also peak demand is not new. So whenever there is a peak demand, one IGG is going to interact with another IGG to share the resources. Okay. So IGG can also allocate resources from a cloud provider. Like it is associated with Amazon EC2, so it can take the resources from Amazon EC2. So integrate allocates and provide a distributed virtual environment. So suppose a customer requests to one IGG and that IGG is not available or not able to provide the resources. So that IGG, okay, has to communicate with other IGG and provide the resources to the customer. But customer is not able to know it is not provided by the IGG which he or she has requested. That's why we call this a distributed virtual environment. So distributed virtual environment manager actually performs this resource allocation and management and takes the decision in collaboration with the other distributed virtual environment managers, right? Just like I told you in the case of task scheduling, one manager server is cooperating to other manager server or concerned with another manager server to provide the resources. So the main core component here is the scheduler. Because scheduler is going to implement the provisioning policy and peering with other gateways. So this is the framework you can see. First is we are requesting the virtual machine to the IGG. If IGG can provide by looking into that, then it will deploy your VM into the physical resources available under that IGG. Right? For this, we have a virtual infrastructure engine. Okay. So the DB manager, actually, that is distributed virtual environment manager, takes this particular decision. If it is not possible in the same IGG, one IGG has to incorporate with another IGG. So it has to communicate with that IGG and provide the resources in another resources. So if you have a traditional infrastructure, for example, a company is having traditional infrastructure and there is no sufficient resources, then that IGG need to another IGG and this IGG may be a part of Amazon EC2. Okay, if traditional way you cannot provide, you can go for the cloud service provider to provide the resources. So finally, if there is a resources is there in one of the IGG, okay, first we will check with this one, otherwise it will check with this one. If it is available, then the application is deployed in this physical resources. In this way, the process is actually carried out. So not only this, you can also go for an email system. Like many organizations, they have their own email system. Jimra is one of the example, right? So where we have millions of users and each and every users are having many emails, right? So we consume a very large disk space for our email system. So this also can be provided by this inter-cloud resource management. If you want to go for web search applications, number of web search per second, it is also varying with respect to time. So we can also perform web searching by taking resources from one IGG and if required, we can connect with other IGG also. Like if you go for Amazon S3, which is a storage one, where we are using SOAP protocol, simple object access protocol to access the objects. So in the Melbourne Research Group is also having a system, they call that is a French Grid 5000 system. So through this system, they illustrate VM creation and management. So we have 3 steps I told you: request of the VM, approve of the VM, and deployment of the VM. Okay, and they reveal major VM management issues and suggest some possible solutions. Okay, they by this grid 5000 system, they identify whenever you are deploying a particular virtual machine or whenever a VM is managed in the system, what are the possible issues that they have identified, and they have suggested some of the solutions. So independent service management is also important, right? One IGG may be work independently, okay, or it will be collaborate with other IGG to provide the resources. So we execute many unrelated tasks. If the tasks are unrelated, means they are independent, right? If they're independent, you can easily execute them without depending on any other IGG or servers, right? But if they are related tasks, you have to look into the dependencies or precedence constraints in order to execute them. Similarly, Amazon Simple Queue service, if you explore, you will get reliable communication service between different providers. If you deal with the multiple providers for multiple services into a single framework, Amazon SQS is able to provide it. So here you can see there are some templates we have, like we have a Ubuntu template with 1 core and 128 megabytes, another template with Fedora, 2 cores with 256 MB, OpenSUSE, that is 1 core 512 megabytes. So based upon whenever you are deploying a VM, you can use one of these template. Okay, any template. If you want to create your own template, you can create it. Okay, otherwise you can go to the template directory and choose an appropriate template which can satisfy your system. Like Amazon EC2 also set up some of the template. Okay, specific template like T2 micro, T2 mini. Okay, so whenever your requirement will have, so based upon your requirement, you can request it, right? So here you have grid 5000 systems, right? So whenever you want a VM instance to launch, you can submit the VM in this format, like vmms.submit VM template and host, that you have to specify and submit. And VM manager service has to take care of this thing, right? It has to look into the template directory. Suppose some template, particular template you have specified, right? Let it be Ubuntu or Fedora or OpenSUSE. Whatever template is there, based upon that, it is going to launch. Again, user has to give, once the work is done, user wants to shut down this instance. That also user can do it. Now, this is the grid 5000 systems. It consists of 4,792 processor cores with 9 grid sites. These guides, these different sites name is Lily, Nancy, Leon, or say Rennes. Okay, others you can say Sophia and other cores. If you sum the number of cores, right? This is you can say this is the map of France, right? They deployed this grid 5000 in the system in across 9 different cities of France. And in each and every sites, you have number of cores. Like here, the number of cores is 568. Here, the number of cores is 574. Together, they have 4792 processor cores in 9 different sites. Right? For example, let's say Sophia is connecting with Orsay, right? So one IGG is connecting with another IGG. These all are IGGs. Okay? So there is 2 gateway. But let's say Sophia, Rennes, and Nancy, they want to communicate. Okay, I'll remove this one. Then there is a 3 gateways. Okay, or now I'll add another one. Let's say Orsay, right? So they 4 makes it a 4 gateways. So together, what they want to do, they want to share the resources so that whenever there is a overflow of the resources, one can communicate with others. And this line, the communication link between these different sites is 10 Gbps link, and they can also go for different kind of peering to share their workloads. So what kind of workload sharing they can do? Here you can see there are 4 different strategies. One is called as a load without peering. Another is called as load when peering. Third is load accepted. Fourth one is load redirected. For example, there are 4 bars you can see, right? In x-axis, you can see these are the different sites, Nancy, Rennes, Orse, and Sophia. Y-axis represent the load. So initial load is this one. First one represent the initial load, which I am strike out here, right? So you can say initially there is a heavy load on Rennes, but there is very less load in Orse. And if you see there are number of cores, Nancy is having 574 cores. Rennes is having 722 cores. Orse is having 684 cores. And Sophia is having 568 cores. So more or less they are having 550, you can say, or 600 cores, something you can estimate, right? So when they are not sharing their workload, you can see the workload is very high. Right? Rennes is having very high workload. Let's say the load is 1.8, whereas Orse is having the workload close to 0. But when they use the strategy from without peering to when peering, so they want to collaborate each other, you can see their workload is actually reduced. You can see this green color one, their workload is more or less. Like here, the workload is very high. Now it is reduced to average one. Here the workload is almost same in the case of Nancy. Orse case, the workload is little bit increased. Sophia case also it is increased. Okay, but you can see whenever you want to go for peering, suppose you want to give your workload to your friend also need to accept it, right? So we also calculated here what is the load accepted. So here you know this machine, this Rennes is having a heavy workload, right? It is having heavy workload. So load accepted is very, very low, right? Load accepted is very, very low because it is already highly loaded. But other like Nancy or you can say Orse or you can say Sophia, they are ready to accept the load because they are underloaded. If some server is underloaded, then only you can actually provide the some load, right? If it is overloaded like this Rennes, it cannot accept other load. Then which site is load redirected? Some loads are also reaching to Rennes even if it is overloaded. So it is redirected at most. Okay, the last bar. And the Nancy case also, you can see Orse case, it is very less because it has not redirected because it has less load, right? Similarly, you can say in the case of Sophia is also it is very low because it can accommodate. If you can accept your own load, then you will not migrate that load to others, right? So in this way, you can see 4 different sites how actually they manages the loads in 4 different situations. What is load without peering, when peering, and load accepted and load directed. These are the 4 different cases. Okay, so this is all for today. We'll stop here. If you have any question, you can ask.